this will be very short. I'm just going to show you a look at the graphs of the solution from that last problem. And so this won't take very long, but I want to show you if you were to solve the original problem that we did in the previous problem by graphing, basically what you would have is this dark, the feasible region would be this dark blue region, and I'm not going to actually go through and solve this, but it would be this dark blue region that runs down through here and kind of goes out through here. And let me make that a little easier to see. So let's make it blue and make it wider. Okay, so there you would have 3 corner points, 0, 20, 9, 2, and 15, 0. And if you plug each one of those values into the objective function, the 5x1 plus 2x2, you would actually get that the minimum is 40, and it occurs at the point 0, 20. But the main thing I want you to realize is that the minimum value for this function is 40. Now, if I solve the dual problem the same way by graphing, now of course if you solve the dual problem, this is really, this would be y1 for the x-axis and y2 for the y-axis. But still, if you actually graphed this, the graph would look something like this. Let me show you the graph here. The graph here would be just a triangle, and it would go like right here. And so the corner points for this triangle would be, triangular region would be 0, 2, 0, 0, and then this point is actually the point 2/3, 0. So if you plug in the point 0, 2, you get p equal 40. If you plug 0, 0 in, you get p equals 0, and if you plug 2/3, 0 in, you get p equals 10. And of course, when I say plug in, I'm talking about plugging it into this value. And notice that, you know, we wanted to maximize the dual problem, and notice that the maximum value of the dual is actually 40. So let me highlight that for you. So the maximum value of the dual problem is 40. So notice that the original problem, the minimum of the original problem when I solved it by graphing was 40. And then the dual problem, when I solved it by graphing, was also 40 for the maximum. So it just goes to show you that I'm not pulling your leg here, that the maximum for your dual problem is going to be the same value as the minimum for your original minimization problem. And so that's really all I wanted to show you on this. So it's not really that important in the scheme of things, but I just wanted you to see this graphically, that these two problems have the same optimal solution. But do notice that the point of where they occur are not the same. So that's why you can't just look at the far right of the tableau when you actually solve your dual problem, because the solution is actually not at the far right, but it's actually at the bottom of the tableau. So I'll go ahead and do some more problems using the dual method in the next video.